So our first topic is motion in one dimension. Just like last year, we're going to start off by talking about vectors and scalars. Remember that vectors have a magnitude and a direction, meaning that it's going to have a sign attached to it. Positive meaning it's moving to the right, negative meaning it's moving to the left. Scalars are only going to have a magnitude, only a numerical value, meaning that it's always going to be positive. So some examples of scalars are time, mass, speed, and distance, where some examples of vectors are velocity, displacement, and acceleration. We also begin with displacement and distance. Displacement is a change in position. So remember that anytime that you see a delta, you always need to think of change in, always final minus initial. In this case, final position minus initial position. Remember that displacement is a vector quantity, meaning this one does need both a magnitude, meaning a numerical value, and a direction. Distance is the length of a path a particle takes, meaning the distance traveled. This one is a scalar, so it will always be positive. So this is a very basic example of displacement. So here you see a little guy going from an initial position of 1 centimeter to a final position of 5 centimeters. So always final minus initial, giving you a displacement of 4 centimeters. Because it is positive, it's telling you that it is displaced to the right of where it began. In the second example, you see our little guy going from 9 centimeter position to 3 centimeter position. So here, our final position is 3 centimeters, so that goes first, minus 9 centimeters, our initial position, giving us a displacement of negative 6 centimeters. That means we are displaced to the left of where we started. For these types of examples, you need to make sure that you put your final position first. That's probably the most common mistake you might make all year. I want you to try this example on your own. This one says, calculate the displacement and distance traveled by the coach at point C and point D. What that means is our coach is starting at position A, going to position B, then C, then D. Be sure to pause the video now and give yourself time to work on this problem. You should have gotten from point A to point C a distance traveled of 55 yards, a displacement of 15 yards to the left. A negative 15 would have also been an accepted value. For part 2, you should have gotten a distance traveled of 95 yards and a displacement of 55 yards to the left. Remember that displacement needs two things, both a magnitude and a direction. Here, negative 55 would have also worked. If you got this, that's awesome. Then go ahead and skip the explanation and move on to the next part. If not, keep watching. So part 1 asks us to solve for the distance traveled between A and C. So we start at A, which in this case begins at position 50. I know that we start at position A because time is equal to 0 here. So we go from position A to position B. We traveled 35 yards in this case. From B, we go to C. And here we travel 20 yards. So total distance is 55 yards. For part 2, we're solving for the displacement from point A to point C. So, from here, we look at the equation for displacement. Final position minus initial position. Our final position is 35 yards. And our initial position was 50 yards. So, our displacement is negative 15 yards. or 15 yards to the left. Either one is telling you that you have been displaced 15 yards from where you began, and you are now to the left of where you began. For the next part, you're trying to solve for your displacement from A to D. Displacement being final minus initial. That's an F. Final position being negative 5 yards. Minus 50 yards, your initial position. So, you get negative 55 yards for your displacement. For your total distance traveled, we know that we had 55 yards to begin with. So from A to C, we had 55 yards. That came from the previous example. So from A to C, we can count that we get 40 yards. So total distance traveled, 95 yards. Our next topic has to do with average speed and average velocity. Average speed is the total distance traveled divided by the total time interval required to travel that distance. It is a scalar quantity, meaning it is always positive. So here, there's just two things you need to remember. Total distance and total time gives you average speed. Average velocity is displacement, delta x, divided by the time interval delta t during which the displacement occurs. So, remember, again, it is a vector, meaning it needs both a magnitude and a direction. Here, you need to be really careful that you use displacement instead of total distance, because they will give you two different numbers. When you're talking about averages, especially for velocity and acceleration, which we'll talk about in the future, it will be represented by a line on top of the V, or AVG for average below, as a subscript. I want you to go ahead and try this example. A motorist drives north at 20 meters per second for 20 kilometers, and then continues north at 30 meters per second for another 20 kilometers. What is his average velocity? If you're having trouble, think of something that you might need to calculate before you calculate average velocity. You should have gotten 24 meters per second as your answer. If you did, go ahead and skip the explanation. For this problem, there's a few things we need to do. First, we need to notice that we're working with meters per second for velocity and kilometers in distance. So we need to make sure that these two are in the same units. It's a lot easier for us to just work in meters per second, so I'm going to go ahead and convert this to 20,000 meters. That's a 20,000. And another 20,000 meters over here. So now we have units at work. So our definition of average velocity is a change in position over a change in time. Displacement over time. So here our displacement is 40,000 meters. So we can go ahead and write that part in. 40,000 meters. But we don't know what our total time is. So this is something that we need to calculate before we can solve for our average velocity. So what we can do is solve for the time it takes to complete the first part of our movement. So we know that speed, or velocity, is equal to displacement over time. If we're trying to solve for time, then we can multiply by t, so that these cancel out, and you get Vt is equal to x. Again, our goal is to get t by itself, so we divide by v, and we get time is equal to displacement over velocity. In this case, 20,000 meters divided by 20 meters per second, which gives us 1,000 seconds. So we traveled 1,000 seconds in the first part of our motion. For the second part, we can use the exact same equation. We don't have to re-derive it. And our displacement was the same. And our speed was 30 meters per second. You should have gotten a time of 666.67. So we have a time for our second segment and a time for our first segment. Because we're trying to solve for average velocity, which is displacement over total time, all we need to do is add these two times together, which gives us 1,666.67. You should get something close to 24 meters per second. Go ahead and try this example. The correct answer is final position is at 7.1 meters. To do that, you need to start out with your equation for average velocity. So v is equal to delta x over t. Yes, this is final time minus initial time. In this case, our initial time is equal to 0, and our final time is 1.6 seconds. So, remember that displacement is actually final position minus initial position. So that's where we can break up these two pieces. So rewriting this, v average is equal to final position minus initial position. We're trying to solve for final position. So what I want to do is multiply by t, so that these cancel. And I'm left with v times delta t is equal to final position minus initial position. Then we add initial position to both sides, and plug in our final numbers. So we had 3.1 meters for our initial position, plus 2.5 meters per second, times 1.6 seconds. Always double check that your units work out. So here, seconds and seconds cancel, and we have meters plus meters gives us meters, which is good because we're solving for a position. And our last example, Penny is moving to the right at 1.8 meters per second, Allie is moving to the left at 1.1 meters per second. Already getting a couple of important pieces of information. To the left, 1.1 meters per second, and to the right, 1.8 meters per second. Because we are talking about velocities, right is going to mean positive, left will mean negative. The two start out 15 meters apart. Moving toward each other, assume that Penny starts at position x initial is equal to 0. How long before they run into each other, and at what position do they run into each other? So for this one, it's always good to draw a picture, like I've included up here. So Penny is moving to the right at 1.8 meters per second. Allie is moving to the left at 1.1 meters per second. I know that they are a dog and a cat because it is my dog and cat. So, when you're thinking of this problem, you want to think of what two things they will have in common. Basically, what is the problem asking for? The time and the position. When Allie and Penny run into each other, they will have the same position, the same final position, and the same time it took to make that collision. So, what that means is we're going to have two equations. So, And I can label this as Penny's information. So P for Penny, P for Penny. I'm not labeling the final position and the final time because this is going to be the same for both. Now I go over here and I did the same thing for Allie. This is an X, I, A, initial position of Allie. Again, time and final position will be the same for both. So I want to solve one in terms of final position. So that means I multiply by t, cross that out, multiply by t, so that I get velocity of Penny times time is equal to the final position of Penny minus the initial position of Penny. Really, this should be just final position. Again, I want to get final position by itself, so I add initial position to both sides. All of these subscripts don't change the value of our variable. It's just telling more information about it. So I'm going to rewrite this over here. So VP times T plus XIP equals XF. Same thing over here. Because in algebra is exactly the same, I'm just going to go ahead and write it what I know it will look like. Now they both have an equation equal to final position. Something that we do very often when you have two equations and two unknown pieces of information, in this case t and final position, we always substitute. Always, always, always. Two equations with two unknowns, substitute. In this case, we are substituting for final position. What that means is we're going to set them equal to each other. Because I know that the final positions are the same. Another thing we can cross out before we start putting in our numbers is the fact that Penny starts off at initial position is equal to 0. So that simplifies our equation even more. I'm going to go ahead and write this on another page. So, velocity of Penny times time is equal to velocity of Allie times time plus the initial position of Allie. And we're trying to get time by itself. So we subtract VAT from one side. This becomes VP times T minus VA times T is equal to XI times A. I know this looks a little weird that we're just working with variables right now, but this is going to be a really important skill that you make sure that you understand. Now that we have a t here and we have a t here, and that's what we're trying to solve for, I'm going to factor out that t. And again, try to get it by itself. So, divide and divide by both sides. So t is equal to the initial position of Allie divided by the velocity of Penny minus the velocity of Allie. In this case, those numbers were 1.8 minus a negative 1.1. And it's important that we put that negative, the fact that she was moving to the left in there, because two negatives here give us a positive. So we get 5.17 seconds, the time it took for them to collide. Now, the second part was asking for the position at which they collide. So because we have two equations that equal position, we can use either one. Pennies will be the easiest because of her initial position. Goodness. Her initial position was equal to 0, so all I need to do is plug in some numbers. 1.8 meters per second times 5.17 seconds gives me 9.306. Or just 9.3, it's fine. Meters. This is the position in which they collide.